In the previous video in this series, we learned about the factors that can affect the rate for an SN1 reaction or an SN2 reaction, and that material is summarized on the screen. In this video, we will see how this material can be tested on problems that are typical of the problems that you might see on your exams. Please pause the video and try this problem. Now we'll discuss it together. Well, we know the way to compare carbocations is by classifying them as primary, secondary, or tertiary. So let's do that. This looks like a primary carbocation. Remember, we're focusing on this carbon because that's the one with the positive charge. This carbon is connected to one carbon chain, primary. This would be a tertiary carbocation because this carbon is attached to three carbon chains. But we should also immediately notice that it's resonance stabilized. So this is tertiary with resonance. Here's another tertiary carbocation. This carbon is connected to three carbon chains, but there's no resonance here. There's no lone pairs or pi bonds that can shift towards the positive charge. And this is what we would call not a primary, but a methyl carbocation, because this carbon is attached to zero other carbon chains. So now to rank these in order of stability, we know that tertiary should be the most stable. Tertiary is the most stable because we know that each of these electron-donating carbon chains helps to stabilize the electron-poor positive charge. Then after tertiary, there should be primary. And then less stable would be the methyl group. I'm arranging the compounds like this from high to low because least stable also means highest energy, and most stable means lowest energy. So for me, it's intuitive to put the most stable low on the page because those are low energy, and the least stable high on the page because those are high energy. Now, how about the tertiary with resonance? Well, we know that the resonance will make this even more stable than an ordinary tertiary. Having the resonance will make this even more stable than an ordinary tertiary carbocation. So I'll write tertiary with resonance at the very bottom of this list for the most stable. Now we can rank these. We know that we want to use the ranking of 1 for the least stable. So this would be a ranking of 1, 2, 3, and then a ranking of 4 for the most stable. And now we can write down our answer. The methyl has a ranking of 1, least stable. Then the primary has a ranking of 2. The tertiary has a ranking of 3, and the tertiary with resonance has a ranking of 4. So here's our answer. That problem gave us a chance to practice what we've learned about how to rank stability of carbocations. We know that substitution with carbon chains stabilizes carbocations because carbon chains are electron donating, but we also learned that resonance can also stabilize carbocations. For simplicity, I didn't specifically include resonance stabilized tertiary carbocations in this list, but it should be obvious that a resonance stabilized tertiary carbocation would be even more stable than an ordinary tertiary carbocation. It's easy to get confused and make careless mistakes on these ranking problems when there's multiple things to compare. So one thing you can do is notice how I tried to be very clear in my work about which was the least stable end of my work and which was the most stable. Write things down to help you avoid getting confused. Pay careful attention to whether you're supposed to rank things in order of increasing or decreasing stability. And just double check when you're done to make sure you didn't make any careless mistakes. 1 is supposed to be least stable. Well, yeah, methyl is the least stable carbocation. Then primary, then tertiary with resonance. Just double check your work on this type of problem because it's easy to make careless mistakes when you're ranking multiple different options. Again, write down notes to yourself to make your notes more helpful. If I hadn't written down which end here was the least stable and which was the most stable, it would be much easier for me to make a careless mistake. Just writing down these little notes makes it much less likely that I'll make a careless mistake. All right, so remember that when you're comparing carbocations, we classify them in terms of primary, secondary, tertiary, and methyl, but we also classify them in terms of whether there's resonance. Here's a question we haven't discussed in these videos. Can you give an example of a Sovolysis reaction? Well, we haven't discussed that yet, so I'll just tell you the answer. SN1 reactions that use the water or alcohol as the nucleophile are an important example of Sovolysis. At this point in the course, if we use the term Sovolysis, basically that means an SN1 reaction using water or alcohol as the nucleophile. Can you see why this is a logical term? It's logical that it has solvo in the name. That refers to the solvent. Remember that water and alcohol are used as solvents. So it makes sense that this has solvo in the name to refer to the solvent. And do you know what lysis means? You should know that lysis means breaking. Well, an SN1 reaction that uses water or alcohol as the nucleophile uses the water or alcohol to break apart the substrate. Here's an example we saw in the previous video. This is an SN1 reaction using water as the nucleophile. And do you see how we're using the water to break this substrate into pieces? We're using this to form a permanent separation between the alpha carbon and the leaving group. At the beginning of the reaction, the alpha carbon is attached to the leaving group, and by the end of the reaction, the alpha carbon is no longer attached to the leaving group because the water has interposed, so to speak. So this would be an example of a solvolysis, using the solvent to break apart the substrate. So again, you should know that at this point in the course, the word solvolysis refers to SN1 reactions that use water or alcohol solvent as the nucleophile. I'm covering this now simply because this is a term that you might possibly see used by your professor on exams, and this was a convenient time to cover that term. Please pause the video and try this problem. Now we can discuss. I guess it would help to put in some numbers. For simplicity, I guess it's not necessary to number these other carbons in this molecule. And I suppose it would help to identify the alpha carbon. The alpha carbon is the carbon attached to the leaving group. So carbon 2 is the alpha carbon in this picture. Carbon 5 is the alpha carbon in this picture. It would help to identify the mechanism. Well, we just learned what Sovolysis is. We just learned that Sovolysis is an SN1 reaction that uses the water or alcohol solvent as the nucleophile. And notice here we do have a water solvent, so it makes sense that we could use water solvent for an SN1 Sovolysis reaction. So notice that when you see this term, that's basically a code that says SN1 reaction. So we want to know, basically this is asking which of these reactions will be the faster SN1 reaction. Well, to compare these, they both have the same leaving group. So we can't compare them based on leaving group because that's the same. And they both have the same nucleophile, water. When you're making a comparison, you have to look for something that's different between the molecules. Well, the thing that's different here is the alpha carbons. And we compare alpha carbons by focusing on primary, secondary, or tertiary. Alpha carbon in compound A is tertiary, because carbon 2 is attached to 3 other carbon chains. The alpha carbon in compound B is secondary, because carbon 5 is attached to 2 carbon chains, one that proceeds clockwise around the ring and one that proceeds counterclockwise around the ring. Well, we've learned that tertiary alpha carbons are better than secondary for SN1. We've learned that tertiary alpha carbons are better than secondary alpha carbons for SN1. So here's our answer. Substrate A undergoes the faster SN1 Sovolysis reaction. Now this wouldn't be a full credit answer because we haven't explained why. So you'd have to articulate why this is faster. So here's a better answer that explains that substrate A is better for SN1 because it has a tertiary alpha carbon, which is better for SN1 than a secondary alpha carbon. This still might not be 100% credit because we still could go deeper into explaining why. Why is a tertiary alpha carbon better for SN1 than a secondary? How would you explain that? So here's a better answer that explains that a tertiary alpha carbon is better for SN1 than a secondary because a tertiary carbocation is more stable than a secondary carbocation. I think this would be a full credit answer. This would be a full credit answer. But even so, just for our own understanding, can you explain why a tertiary carbocation is more stable than a secondary? So here's even more detail about why tertiary carbocations are more stable. It's because carbocations have too few electrons, and carbon chains help to stabilize that because they are electron donating. A tertiary carbocation has one extra carbon chain that a secondary doesn't, and that extra carbon chain helps to stabilize the carbocation by donating electrons to the carbocation. Here there are 3 carbon chains surrounding the carbocation that can stabilize the carbocation by donating electrons to it. Here there are only 2 carbon chains surrounding the carbocation that could stabilize the carbocation by donating electrons to it. Okay, this is probably a lot more detail than you would need for a full credit on an exam problem. Probably this would be enough for full credit, but it's good to go through all the details to make sure you actually have understanding of the material. Notice that it would be hard to get this problem correct if you didn't know what the term savolysis means. So make sure that you have memorized that savolysis refers to SN1 reactions using water and alcohol solvents. At least that's the main use of the term at this point in the course. So earlier we have learned this pattern for which alpha carbons are best for SN1. Tertiary alpha carbons are better than secondary alpha carbons for SN1. And this problem is an example of how that idea could be tested on an exam. Please pause the video and try this problem. Now let's discuss. We could start by numbering the carbons. Normally it would be a mistake to use the same numbers for different compounds. Normally I wouldn't use the same numbers for different compounds. But since these compounds are so similar, and since our goal is to compare the compounds, since our goal is to compare these, I think on this problem it will be helpful to use similar numbers for the 2 compounds. Okay, so now we can start comparing these. I guess we can identify some roles. We would expect neutral bromine to play the role of leaving group. We would expect this alcohol to play the role of nucleophile. Now, do you understand what the ET means? You should know that ET is an abbreviation for ethyl. So the ET just stands for an ethyl group. So this is just an alcohol that has a ethyl group, ethyl alcohol. So this is just a normal alcohol solvent that has 2 carbons. And do you know what the triangle symbol means? You should know that this triangle symbol in chemistry stands for heat. So this is a reaction where we are heating up the starting materials. It turns out that that's not going to play any important role in our solution to the problem. We should label our alpha carbon. The alpha carbon in this picture is carbon 4. And in this picture, the alpha carbon is carbon 3 because those are the carbons that are attached to the leaving group. Now we should determine the mechanism. Should we use the table? Should we use the table to determine the mechanism? No, because the problem told us the mechanism. If the problem tells you the mechanism, then you don't use the table. Instead, you use the mechanism from the problem. So we know that both of these reactions will be occurring through a SN1 reaction because the problem told us so. I applied that same idea to this problem. I didn't use the table to determine the mechanism here. I just said it was SN1 because the problem mentioned savolysis, and we know that's SN1. Now, to determine which of these is faster, we have to look for some difference between these 2 compounds. It's useless to compare the leaving groups because they have the same leaving groups. It's useless to compare the nucleophiles because they have the same nucleophiles. But they do have different alpha carbons. Here the alpha carbon is carbon 4. Here the alpha carbon is carbon 3. So we should compare those alpha carbons and decide which is better for SN1. Well, we'll start by checking for primary, secondary, or tertiary. Carbon 4 is a secondary alpha carbon because it's attached to 2 carbon chains. But carbon 3 is also a secondary alpha carbon, because carbon 3 is also attached to 2 carbon chains. Well, that doesn't help us because remember we're trying to find some way in which these compounds are different. Well, they both have alpha carbons that are secondary, so that's not a difference between them. So how are the alpha carbons different? It might be obvious to you. It might be obvious to you how the alpha carbons are different. But if not, it would be helpful to start going through the mechanism. So let's start going through the mechanism here and see if that helps us to see how these compounds are different. It's an SN1, and we know that the first step for an SN1 is for the leaving group to leave. Remember, the most important thing is to change charges. When the alpha carbon loses its bond, it changes from neutral to positive. So make sure you show the positive carbocations. Now, both of these carbocations are secondary, but we know that something else that influences a carbocation besides its substitution is whether there's any resonance. And I hope that you can recognize that there are no other resonance structures for this intermediate, but there is another resonance structure for this intermediate. There's another resonance structure for this intermediate that we can get by using electron pushing arrows that look like this. Notice that based on this electron pushing arrow, carbon 1 loses electrons to become positive, and carbon 3 gains electrons to become neutral. So you can see this carbocation is resonance stabilized because the positive charge is spread out between carbon 1 and carbon 3. This carbocation is not resonance stabilized. It's too far from the pi electrons to participate in resonance with those pi electrons. Carbon 4 is too far from these pi electrons to participate in any resonance with the pi electrons. Resonance structures involve the movement of pi electrons. So here would be a good answer. Notice that it's not enough to say that reaction B is faster. You must justify your answer for full credit. This would be a good justification. I would encourage you on this problem to actually draw the carbocations and draw these two resonance structures as part of your explanation. That might be more detail than the professor requires, but the professor might appreciate that detail, and it helps you to make sure that you actually understand this material. So what I have written down here on the screen would form a good explanation for this problem. So notice that it can be helpful to draw part of the mechanism, even if the question doesn't specifically require it. It helped us to draw the first step of this mechanism so we could form the carbocation and then show that this carbocation has resonance and this one does not. Earlier we learned that substitution stabilizes carbocations, but we also learned that resonance stabilizes carbocations. And this problem gave us a chance to practice the idea that resonance stabilizes a carbocation. A lot of students would not get this correct because most students don't even think about resonance unless they see the word resonance in the problem. Notice that this problem never mentioned the word resonance. We had to think to use the concept of resonance on this problem, even though it wasn't mentioned in the problem. Look for opportunities to apply resonance when you're solving problems. Remember, it would help here to know what the ET stands for. ET stands for an ethyl group. So this is ethyl alcohol. Remember, the triangle here stands for heat. This is a reaction. These reactions took place in the presence of heat. That didn't turn out to have any significant impact on how we solved the problem. By the way, here's a table that you might find useful in your organic chemistry class. Oftentimes in Ochem, you'll see exam problems that ask you to explain something, like the previous problem. So what factors should you consider for trying to explain things? So this is a checklist that you should consider when you have to explain something in organic chemistry. Of course, the most important thing to think about is formal charges. First, think about formal charges. But maybe the second most important thing to think about is resonance. Think about whether resonance plays a role. Remember that if resonance does play a role in a reaction, it's usually the most important factor. Steric hindrance plays an important role in organic chemistry. Also sometimes electronegativity, delta charges, molecular geometry. So it's useful to have this checklist that you can run through in your head if you're given a question like this previous one where you have to explain or justify something. Obviously, this is far from complete. There are many other factors. There are many other factors that might sometimes be important in Ochem. These are just some of the most important factors that occur to me right now. So I suggest that this would be a useful table to have in your notes. If you see an Ochem problem where you need to explain why something happened or didn't happen, it's useful to run through these factors and ask whether any of them are applicable for the problem. Obviously, for the problem we just worked with, the key factor was that one structure had resonance in the carbocation and the other structure did not have resonance in the carbocation. Remember that when you're comparing two structures or two reactions, you have to look for a way that they're different from each other. This is a variety of different ways in which two reactions or molecules could be different from each other. Please pause the video and try this problem. Now we'll discuss. We could start by numbering the carbons. In this case, it makes sense to give different numbers to the two different molecules. Then I guess we can start by identifying our roles. We would expect the chlorine to be our leaving group and the water to be our nucleophile. Carbon 7 here will be the alpha carbon, and carbon 10 here will be the alpha carbon, because those are the carbons attached to the leaving group. We need to identify the mechanism, but we're not going to use the table. We won't use the table for identifying the mechanism. Instead, the problem tells us. The problem tells us that this mechanism is an SN1 mechanism. Now we look for a difference between these two reactions. Well, they have the same nucleophile and the same leaving group, so let's compare the alpha carbons. The alpha carbon for reaction A is a primary alpha carbon, and the alpha carbon for reaction B is a secondary alpha carbon. So you might think that reaction B will be better for SN1 because we know that secondary alpha carbons are better than primary alpha carbons for SN1. But remember, we've learned that there's another factor that affects the alpha carbon. It's not just whether it's primary, secondary, or tertiary. You also have to check whether the carbocation has any resonance stabilization. So let's not end the problem too soon. Let's go further and see if either carbocation would have resonance stabilization. So the mechanism for the first step of the reaction would look like this, and we can draw the carbocation intermediate. Remember that after the alpha carbon loses electrons, it forms a carbocation intermediate. Now you might think that a secondary carbocation is better than a primary, but remember we also have to check for resonance. And this carbocation is close enough to these pi electrons for there to be resonance structures. Can you draw the electron pushing arrows for that? So here's what the electron pushing arrow would look like. By the way, notice that this arrow is wrong. This arrow is wrong. You should not draw the arrow pointing directly to carbon 7. Instead, it should point to the bond between 1 and 7, because that's how you show that you're forming a pi bond. The way to show that you're forming a pi bond is to show the arrowhead pointing between the two atoms. So that gives us another resonance structure. Remember to change two charges. The atom at the end of the arrow, carbon 7, changes its charge, and the atom that loses electrons at the beginning of the arrow, carbon 6, changes its charge. So clearly this carbocation is resonance stabilized. In fact, there's even two more resonance structures. Here are all the electron pushing arrows to show all those different resonance structures. Notice that each electron pushing arrow, the arrowhead is pointing to a bond. Arrowhead pointing to a bond. Arrowhead pointing to a bond. Because that's how you draw an electron pushing arrow that shows the formation of a pi bond. Okay, so clearly this carbocation is far more stabilized than an ordinary primary carbocation. This is an extremely stable carbocation because it's spread between 1, 2, 3, 4 different resonance structures. The positive charge is spread between carbon 7, carbon 6, carbon 4, and carbon 2. That's going to be far more stable than this carbocation, which is concentrated just on carbon 10. There are no additional resonance structures for this carbocation because there are no pi electrons to move around in this molecule. Remember that resonance structures have to involve the movement of pi electrons. To put that in more usable terms, resonance structures involve the movement of pi bonds and lone pairs. Resonance structures involve the movement of pi bonds and lone pairs, and we don't have an opportunity for either of those things here. All right, so it should be clear that reaction A will be faster because it forms the more stable carbocation. Here's our answer. Reaction A is faster. Remember, you must justify your answer for full credit. So reaction A is faster because this alpha carbon forms a resonance-stabilized carbocation, and this alpha carbon forms a carbocation with no resonance stabilization. And it might help you to get the credit if you draw at least one of these resonance structures. So it might definitely help here to draw the first step of the mechanism to show the carbocation, and then draw at least one of these resonance structures to show the resonance stabilization for reaction A that's lacking with reaction B. Notice there's a trap here. I bet a lot of students thought that reaction B would be faster because it has a secondary alpha carbon, whereas this one is primary. You also have to consider resonance, and just as a problem-solving tactic, when a problem involves resonance, it's usually the most important factor in the problem. On introductory Ochem exam problems, when the problem involves resonance, that's usually the most important factor. So the resonance here is more important than primary versus secondary. We learned earlier that a primary alpha carbon that forms a resonance-stabilized, carbocation is more stable than a secondary alpha carbon. And this particular primary carbocation is especially stable because it forms not just one additional resonance structure, but 3 additional resonance structures. Notice again that the problem never mentioned the word resonance. It was up to us to think about resonance on this problem, although it wasn't specifically mentioned. Resonance is a factor that you should always be on the lookout for in Ochem problems. Remember that this problem involved an SN1 mechanism. And what is the big obstacle to SN1? The big obstacle for SN1 is stabilizing the carbocation. So for that problem, the SN1 reaction that was faster was the SN1 reaction that allowed a more stable carbocation. When thinking about SN1, focus especially on the big obstacle to SN1, stabilizing the carbocation. You can stabilize the carbocation with a more substituted alpha carbon, but you can also stabilize the carbocation with resonance stabilization. Please pause the video and try this problem. Now we can start by numbering the carbons. Normally I would give different numbers to these 2 different molecules, but because these 2 molecules are so similar and because our whole goal is to compare these 2 molecules, I think here it's helpful to give similar numbers to the 2 compounds. We don't need to look for ionic bonds because the ionic bond was already drawn in for us with the formal charges. And we don't need to use our table to determine the mechanism because the problem told us the mechanism. We don't use our table here to figure out the mechanism because the problem told us the mechanism. So to figure out which of these SN2s will be faster, we have to look for a way that the starting materials are different in these 2 reactions. I guess I'll go ahead and label the roles. We expect that this O- will be the nucleophile because of its negative charge. This will be a solvent that doesn't participate in the reaction. We expect the Br will be our leaving group. Neutral bromine is a good leaving group, which makes carbon 3 our alpha carbon. Carbon 3 will have a delta positive and be the electrophile. Now it doesn't help to compare the leaving groups for this problem because both leaving groups are the same, neutral bromine. It doesn't help to compare the nucleophiles because both nucleophiles are the same, CH3O-. So it looks like we'd like to compare the alpha carbons, but it looks like the alpha carbons are also very similar. Both of these alpha carbons are primary. Here's a primary alpha carbon, and here's another primary alpha carbon. In fact, really the only difference here is at carbon 2. The only way these starting materials are different is at carbon 2, so clearly we have to compare which of these carbon 2s is better for an SN2 reaction. Well, what is the big obstacle for an SN2 reaction. You should have memorized that the big obstacle for SN2 is steric hindrance. So we should be asking whether we can use steric hindrance to explain why one of these reactions might be faster than the other. Well, isn't it clear that this carbon-2 is going to provide more steric hindrance than this one? Carbon-2 in this picture is tertiary. Carbon-2 in this picture is a tertiary carbon. But in this picture, carbon-2 is secondary. Well, since there are fewer carbon chains around carbon-2 in this picture, there's less likelihood that these carbon chains can get in the way and block the nucleophile from attacking carbon-3. So, for example, in this picture, it's possible that sometimes carbon-1 is going to rotate into a position where it blocks carbon-3 and makes it difficult for the nucleophile to attack carbon-3. On the other hand, in other cases, carbon-1 might be rotated away from carbon-3 so that it doesn't block carbon-3. But in this picture, there are two methyl groups that could rotate into a position to block carbon-3. Methyl group 4 could rotate into a position to block carbon-3, and when methyl group 4 is not rotated into that position, methyl group 1 could rotate into a position to block carbon-3. So with those two separate methyl groups that could block carbon-3, there's more steric hindrance in this molecule and less in this molecule. Of course, we know that we primarily focus on steric hindrance from the alpha carbon. Usually we focus primarily on steric hindrance from the alpha carbon, but steric hindrance from the next door carbon can also sometimes play a role, and clearly that's what we need to focus on for this problem. So here's our logic. This starting material has less steric hindrance at carbon-2 that could block the nucleophile from attacking carbon-3. And therefore, we have a faster SN2 in this case. And this molecule has more steric hindrance at carbon-2 that could block the nucleophile from attacking carbon-3, which gives this reaction a slower SN2 reaction. Remember, the big obstacle to SN2 reactions is steric hindrance. So here's our answer. Reaction B will have the faster SN2 rate, because for reaction B, carbon-2 has less steric hindrance that can block the nucleophile from attacking carbon-3. Remember, you have to justify your answer to get full credit for this problem. By the way, there's another way to describe this situation. We know that carbon-3, which is attached to the leaving group, is called the alpha carbon. What's a good name for carbon-2? Well, a good name for carbon-2 would be the beta carbon. The carbon that's attached to the alpha carbon can be called the beta carbon. So we can call carbon-2 the beta carbon because it's attached to the alpha carbon. Carbon-2 is the beta carbon because it's attached to the alpha carbon. So then we could say here that, it's the beta carbon that's tertiary in this picture and the beta carbon that's secondary in this picture. In this picture, the beta carbon is tertiary, whereas in this picture, the beta carbon is secondary. And that gives us another way to describe our reasoning. Now we can say that reaction B is faster because for reaction B, the beta carbon has less steric hindrance that could block the nucleophile from attacking the alpha carbon. So this would be a good way to phrase our answer to the question. Of course, this would also be acceptable. So either of these two ways of phrasing the answer would be acceptable. So we've learned that the alpha carbon is the carbon that's attached to the leaving group, and the carbon that's attached to the alpha carbon can be called the beta carbon. There are some other topics in Ochem where that's useful terminology. In the past, we've generally focused the most on steric hindrance from the alpha carbon. Usually we focus most on steric hindrance from the alpha carbon, but steric hindrance from other carbons, such as the beta carbon, can also sometimes play a role in affecting the rate of a reaction. Now, the main purpose of this video series is to focus on SN1 reactions, but when you take your exam, you're going to have to move back and forth between SN1 reactions and SN2 reactions and other types of reactions. So it's important sometimes in these videos not just to talk about SN1, but also to switch gears and make sure that we can switch gears to answering questions about other types of mechanisms. So we need to be able to go back and forth between questions about SN1 reactions and questions like this one that's about SN2. Remember that the big obstacle to an SN1 reaction is stabilizing the carbocation. But the big obstacle to an SN2 reaction is steric hindrance that blocks the nucleophile from joining the alpha carbon. So when we worked on this problem that involved an SN1 mechanism, we focused on which reaction would have a more stabilized carbocation intermediate. Because the big obstacle to SN1 is stabilizing the carbocation. But then when we switched gears and shifted to this problem, which was dealing with an SN2 mechanism, here we focused on which starting material would have less steric hindrance that could block the nucleophile, because we know that the big obstacle for SN2 is steric hindrance that blocks the nucleophile. So make sure you pay close attention to whether each problem is about SN1 or SN2 so that you can switch gears in your mind between those two different ways of thinking about the factors that can affect mechanisms. Please pause the video and try this problem. Now let's discuss. We can start by numbering the carbons. Because this molecule and this molecule are identical, and because our goal is to compare them, I've given them the same numbers. There are no ionic bonds in this reaction, and we're told the mechanism. We're not going to use the table. We won't use the table for the mechanism because the problem tells us that the mechanism will be SN1. Label some roles. There are no negative atoms to act like nucleophiles, so we can use neutral atoms as nucleophiles. A neutral oxygen has a lone pair and can be used as a nucleophile. A neutral sulfur also has a lone pair and can also be used as a nucleophile. In this video series, we've mainly been using neutral oxygen as our neutral nucleophile. But earlier we've seen that there are other neutral atoms that can also function as nucleophiles because of their lone pairs, nitrogen, sulfur, and phosphorus. So a neutral sulfur with its lone pair can act like a nucleophile. We can identify the neutral iodide as the leaving group, and that allows us to identify our alpha carbon as carbon 3. Now, to compare these reactions, we have to look for the difference between the reactions. It's useless to compare the leaving groups because they both have the same leaving group. It's useless to compare the alpha carbons because the alpha carbons are identical. They're both secondary alpha carbons. So what is the difference? The difference is the nucleophiles. Here we have the neutral sulfur as a nucleophile, and here we have neutral oxygen as a nucleophile. Now you should know that neutral oxygen is a poor nucleophile. And you should know that neutral sulfur is a good nucleophile. How? How should you know that? You should know that because you should have memorized this table. You should have memorized that the neutral oxygen in an alcohol is a poor nucleophile. And you should have memorized that neutral sulfur is a good nucleophile. So from memorizing the table, we know that this is a good nucleophile and this is a poor nucleophile. Notice that there are some neutral atoms that are good nucleophiles. Most good nucleophiles have negative formal charges, but there are a few neutral atoms that can also be good nucleophiles. Okay, so reaction A has the better nucleophile. Does that mean that reaction A will occur more quickly? Well, not so fast. We have to ask, does nucleophile quality matter for an SN1 reaction? Does nucleophile quality matter for an SN1 reaction? Remember, we learned earlier that nucleophile quality does not matter for an SN1 reaction. That might seem strange, but remember the reason for that is that the nucleophile doesn't participate in the rate-determining step. Here's the rate-determining step for SN1, and you can see that the nucleophile is playing no role in this rate-determining step. Well, remember, anything that does not affect the rate-determining step will not affect the rate of the reaction. So improving the nucleophile quality does not increase the rate of an SN1 reaction because the nucleophile doesn't participate in the rate-determining step. So here's our answer. Both of these SN1 reactions occur at the same rate. Remember, for full credit, we have to justify our answer. While reaction A does have a better nucleophile, but that doesn't matter for SN1. Nucleophile quality doesn't affect the rate for SN1 because the nucleophile doesn't participate in the rate-determining step for SN1. Did you get this problem right? This problem is a good test of whether you were really understanding the material about factors that affect SN1 reactions that we covered in the previous video. Finally, by the way, what does this triangle mean? Well, you should know that the triangle means heat. These are reactions where we're adding heat to the starting materials. Notice that didn't really have any effect on how we solved the problem. Now, in this problem that we just completed, we saw that this compound was a better nucleophile than this compound. We were able to tell that this was a better nucleophile by looking at our table. But so far, we haven't given an explanation for why this compound is a better nucleophile than this compound. We didn't really need to understand that for this problem. But there are other problems. There are other problems where we would be required to give an explanation for why this compound is a better nucleophile than this one. And it's not good enough just to say that we know that from our table. So the next thing we have to discuss is why is this compound a better nucleophile than this one? So this would be a good time for you to pause the video and see if you already know the explanation. I actually already talked about this in the SN2 series. Do you know the reason why this compound is a better nucleophile than this one? Well, here's the answer. When we compare these two compounds, we notice that the difference between the compounds is that one of them contains a neutral oxygen and one contains a neutral sulfur. So let's find oxygen and sulfur in our periodic table. Here are oxygen and sulfur in our periodic table, and we can see that they are both in the same column of the periodic table. So for nucleophilability, it turns out that what matters when you're comparing elements in the same column is that elements that are further down in a particular column are larger atoms. Sulfur is a larger atom, and oxygen is a smaller atom. And it turns out that for neutral nucleophiles, larger atoms are better nucleophiles, and smaller atoms are worse nucleophiles. To repeat, for neutral nucleophiles, larger atoms further down in the periodic table are better nucleophiles, and smaller atoms further up in the periodic table are worse nucleophiles. Notice that this is specifically the pattern for neutral nucleophiles. That's what we're dealing with here, a neutral oxygen and a neutral sulfur. The pattern for negative nucleophiles is more complicated. The pattern for negative nucleophiles depends on the solvent. I'm not going to get into those issues in this video. If you want more information about comparing negative nucleophiles, you should be able to find that in your textbook. This is the pattern for neutral nucleophiles. Now, why is the larger atom the better nucleophile? It's because the larger atom is more polarizable. Now, obviously, that raises the question, what is polarizability and why does that make something a better nucleophile? But I'm actually not going to go into those details in this video because you're usually not going to be tested directly in any more detail than I've already discussed about these issues. What I have here on the screen will usually be enough information to get problems right that involve comparing neutral nucleophiles. So this information would be enough for most professors for most courses. to get full credit for questions that are asking about neutral nucleophiles. And if you'd like to learn more about this concept of polarizability and how it affects nucleophile ability, you should be able to find more information about the concept of polarizability in your textbook. For most courses, therefore, it'll be good enough if we simply memorize that when you're comparing neutral nucleophiles in the same column of the periodic table, nucleophile ability increases as you move down the periodic table. And usually it will be enough on exams simply to say that that's because the elements further down in the periodic table are more polarizable. So we can say that this compound is a better nucleophile than this compound because the sulfur is more polarizable than the oxygen. So now would be a good point to pause the video and memorize this pattern for comparing neutral nucleophiles in the same column of the periodic table. When we are comparing nucleophile ability for neutral nucleophiles with elements from the same column of the periodic table, the key factor to focus on is atomic size. The larger atom makes the better nucleophile. This rule is based on the atomic size of the specific atom in the nucleophile that will be donating its electrons. The rule does not refer to the size of the entire nucleophilic molecule as a whole. A larger atom makes a better nucleophile. But you should not assume that a larger molecule will be a better nucleophile. Please pause the video and try this problem. Now let's discuss the solution. We can start by numbering all the carbons. We can identify the mechanism. Now we don't use our table for the mechanism. The problem tells us the mechanism. Remember, don't use the table for the mechanism if the problem tells you the mechanism. Here we're focusing on SN2. We can identify our roles. Neutral oxygen will be our nucleophile here, and neutral sulfur will be our nucleophile here. Neutral sulfur and neutral oxygen can both be nucleophiles because of their lone pairs. Our leaving group will be the neutral iodide, and therefore carbon 3 will be our alpha carbon. Now we need to look for a difference between these two reactions. Well, the leaving groups aren't different. The leaving groups are the same. The alpha carbons aren't different. They're both primary alpha carbons. So we have to focus on the difference in the nucleophiles. And we should know that sulfur is a good nucleophile. Whereas, I should say, neutral sulfur is a good nucleophile, whereas neutral oxygen is a poor nucleophile. Remember, the most important thing to focus on is formal charges. So you shouldn't say that you're comparing sulfur and oxygen. You should say that you're comparing neutral sulfur and neutral oxygen. Always focus on the formal charge. How do we know that neutral sulfur is a good nucleophile and neutral oxygen is a poor nucleophile? Well, we discussed that same issue in the previous problem. In the previous problem, we saw that we can use the table to remind ourselves that neutral oxygen, such as in an alcohol, is a poor nucleophile, and neutral sulfur is a good nucleophile. You should have that information from the table memorized. Now, does nucleophile quality affect the rate of an SN2 reaction? Well, yes, we've learned that nucleophile quality does affect the rate for SN2. In the previous video, we learned that nucleophile quality does matter for the rate of an SN2 reaction. Why? Because the nucleophile participates in the rate-determining step for SN2. You can see that the nucleophile does participate in the rate-determining step for SN2, so having a better nucleophile allows an SN2 reaction to proceed more quickly. So here's the beginning of our answer for this problem. We've decided that reaction A will have the faster SN2 rate, but remember that we need to justify our answer. Well, we begin our justification by saying that reaction A is faster because it has a better nucleophile. And we can also say that that matters, nucleophile quality matters here, because we're doing an SN2 reaction, and the nucleophile participates in the rate-determining step for SN2. But even this is probably not a full credit answer. Most professors would want you to also explain why this compound is a better nucleophile than this one. And we learned how to explain that a little bit earlier. Here we're comparing neutral nucleophiles. The difference between these nucleophiles is that one has sulfur and one has oxygen. And sulfur and oxygen both appear in the same column of the periodic table. Well, we've learned that when you compare neutral elements from the same column of the periodic table, nucleophile ability increases as you move down the periodic table because larger elements are more polarizable. So here's our complete answer. Sulfur is the better nucleophile because sulfur is more polarizable than oxygen. Remember that we saw earlier in this video that when you compare neutral nucleophiles from the same column of the periodic table, nucleophile ability increases as you move down the periodic table because larger atoms are more polarizable. The information that I've written down in this answer would be sufficient for most professors in most courses to get full credit on this problem. But remember, if you'd like to learn more about what polarizability is and why something that's more polarizable is a better nucleophile, you can find that information in your textbook. It's important for you to compare our answer for this problem with the answer from the previous problem. These two problems seemed very similar, but they had quite different answers. In both cases, reaction A had the better nucleophile. But in this problem, both reactions occurred at the same rate. And in this problem, reaction A occurred faster. And the reason for that difference is that this problem dealt with an SN1 mechanism, where nucleophile quality does not affect the rate of the reaction, whereas this problem asked about an SN2 mechanism, where nucleophile quality does affect the rate of the reaction. Nucleophile quality does not matter for an SN1 reaction, because the nucleophile does not participate in the rate-determining step for SN1, but nucleophile quality does matter for SN2, because the nucleophile does participate in the rate-determining step for SN2. An important lesson of these two problems is that when you take your exams, it's important that you are able to keep switching gears back and forth between problems about SN1 mechanisms, problems about SN2 mechanisms, and other problems about other mechanisms that you'll be learning about in your class. You'll see a variety of problems about a variety of mechanisms, and you have to keep switching gears between those different mechanisms. So it was crucial on these two problems to identify which mechanism the problem was about. That should have been pretty easy on these problems because the problem told us the mechanism. So always study the information in the problem carefully to see if it gives you any important clues about what mechanism you'll be applying. Here the problems told us directly that we were using here an SN1 and here an SN2 mechanism. Please pause the video and try this problem. Now here's the solution. We can start by numbering the carbons. There are no ionic bonds. These are covalent bonds because hydrogen is a non-metal, and sulfur and oxygen are non-metals, so there's no formal charges. We can use these neutral atoms as the nucleophiles. Neutral oxygen can be used as a nucleophile, and neutral sulfur can also be used as a nucleophile because both of them have lone pairs to donate. We expect that we're going to use the neutral chlorine as our leaving group. That will make carbon 1 into the alpha carbon. So we see that we have a tertiary alpha carbon in both cases. Carbon 1 is tertiary, attached to 3 carbon chains, carbon 6, carbon 5, and carbon 2, a tertiary alpha carbon. We have to choose the mechanism. Well, the problem here does not tell us the mechanism, so we have to use the table to figure out the mechanism. We're in the bottom row of the table because we have a tertiary alpha carbon. Now, in reaction A, we're using neutral sulfur. as our nucleophile. That puts us in the middle column, and that means we would be in this cell of the table. On the other hand, for reaction B, we're using the neutral oxygen in water as the nucleophile. That would put us in this left-hand column, which would mean we're using this cell. But notice that in both cases, the same mechanisms are predicted. So the table predicts the same mechanisms for reaction A and reaction B. And we expect that this is going to be a substitution reaction, not elimination. You can see it really is substitution because we're substituting the sulfur nucleophile for the chlorine. From the product that was drawn for you here, you can see the sulfur nucleophile has been substituted for the chlorine. And in this case, you can see that the oxygen nucleophile is being substituted for the chlorine. Notice that on this problem, they drew the products for us. Remember that after this neutral nucleophile attacks, it's going to have a positive formal charge, which it can get rid of by losing a proton. That's why this oxygen has one fewer proton than this one. And again, after this neutral nucleophile attacks, it can it'll have a positive formal charge, which it can get rid of by losing a proton. That's why this sulfur has one fewer proton than this one does. So it doesn't look like we're using the E1 mechanism here. This looks like a substitution mechanism based on the products. So in both cases, we expect we're getting a SN1 reaction. The table tells us the mechanism will be SN1 rather than SN2. Again, for reaction A, we're in the bottom row for a tertiary alpha carbon, and neutral sulfur puts us in the middle column. That puts us in this cell with an SN1 mechanism. All right, now we have to look for some difference between these two reactions. It doesn't help to compare the leaving groups because the leaving groups are the same. It doesn't help to compare the alpha carbons because the alpha carbons are the same. They're both tertiary. We have to compare the nucleophiles. And we know that this neutral sulfur is a good nucleophile. Neutral sulfur is in this middle column for a good nucleophile. Whereas the neutral oxygen in water is in this left-hand column, and we've learned that that makes it a poor nucleophile. So our first instinct might be that reaction A will be faster because it has a better nucleophile. But wait, does nucleophile quality matter for an SN1 reaction? No. We've learned that nucleophile quality does not matter for an SN1 reaction because the nucleophile does not participate in the rate-determining step for an SN1 reaction. Nucleophile quality does not matter for an SN1 reaction. So we expect that even though reaction A has a better nucleophile than reaction B, reaction A will occur at the same rate as reaction B because the nucleophile quality doesn't affect the rate for SN1. So here's our answer. Both reactions occur at the same rate. Make sure you justify your answer. Reaction A has a better nucleophile, but that's not going to affect the rate for this SN1 reaction because the nucleophile does not participate in the rate-determining step for SN1. In your answer for this type of rate problem, make sure that you specifically mention the name of the mechanism. If you don't specifically say that this is a reaction with an SN1 mechanism, you will probably lose credit because the nature of the mechanism is a big factor in determining the answer to the problem. Well, this problem was quite similar to the two previous problems that we just did previously in this video. Here's the difference. For this problem, we had to use the table to determine the mechanism. This problem didn't tell us the mechanism, so we had to use the table to determine that the mechanism was SN1. For the two previous problems, the problem told us the mechanism. This problem told us the mechanism was SN1. This problem told us the mechanism was SN2. So we didn't have to use the table to determine the mechanism for these two problems. But this last problem did not tell us the mechanism, so we did have to use the table to determine the mechanism. That was very important, right? That was very important because the answer to this type of question is completely different for an SN1 problem and for an SN2 problem. We know that for an SN1 problem, the nucleophile does not affect the rate. But we also know that for an SN2 problem, the nucleophile would affect the rate. So it was absolutely vital that we used the table to determine the mechanism. If the mechanism had turned out to be SN2, our answer would be quite different for this problem. So for these types of rate problems, always make sure that you're clear what the mechanism is for one of these rate problems. Always make sure that you're clear what the mechanism is, either because the problem told you the mechanism or because you used the table to figure it out. And also notice again, if the problem shows you the products, when the problem shows you the products, that can give you a little bit of an extra clue for figuring out the mechanism. We knew the mechanism here was substitution and not elimination by looking at these products. Please pause the video and try this problem. Now let's discuss together. Let's start by numbering. Notice that I was careful not just to number these carbons, but also to number the carbons in the products. That makes it easier for me to see what changes have occurred from the starting materials to the products. We should look for ionic bonds. There are no ionic bonds here. All the atoms are non-metals, so all the bonds are covalent, so there's no ionic bonds and no formal charges that we need to draw in. So now we can try to identify some roles. There are no negative atoms to play the role of nucleophile, so we'll look for a neutral nucleophile. Well, we know that neutral phosphorus and neutral nitrogen can both play the role of nucleophile because of their lone pairs. So we expect the phosphorus and the nitrogen to play the role of nucleophile. We should recognize this large group as a sulfonate. So these starting materials are alkyl sulfonates, carbon chains attached to sulfonate groups. We know that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So in this sulfonate, the alpha carbon is carbon 3 attached to the oxygen. This carbon attached to the sulfur is not the alpha carbon. That means that we can identify this oxygen attached to the alpha carbon as our leaving group atom. Remember that sulfonate groups are good leaving groups. Now we need to determine the mechanism. Notice that the problem did not directly tell us the mechanism. The first thing for identifying the mechanism here is to look at the products. Since the products are shown, that gives us a clue about the mechanism. And from these products, we can see that both of these reactions are substitution reactions. We can see that in both cases, the leaving group is leaving the alpha carbon, and the nucleophile is attaching to the alpha carbons. These both look like substitution reactions, but in order to determine whether they're SN1 or SN2, we will have to use our table. We should identify that we're dealing with primary alpha carbons. This alpha carbon is attached to one carbon chain. That puts us in the top row of the table. Now for reaction A, the nucleophilic atom is neutral phosphorus. And we can find neutral phosphorus in the middle column of our table. And for reaction B, the nucleophilic atom is neutral nitrogen. And you can also find neutral nitrogen, here's neutral nitrogen, also in the middle column. Both reactions will use this middle column of our table, and therefore the table predicts that for both reactions the mechanism will be SN2. So we should make sure that we write down that the mechanism we're considering here is an SN2 mechanism. We can take an extra step and identify carbon 3 as the electrophilic atom for both of these mechanisms. Now we have to decide which mechanism is faster. Well, it doesn't help to compare the leaving groups because both reactions use the same sulfonate leaving group. It doesn't help to compare the alpha carbons because both reactions use a primary alpha carbon. The difference between these reactions is the nucleophile. So we have to decide which of these is the better nucleophile. We know that nucleophile quality does matter for the rate of an SN2 mechanism. We know that for an SN2 mechanism, the quality of the nucleophile does matter because the nucleophile participates in the rate determining step for SN2. So we have to decide which of these nucleophiles is the better nucleophile. Now we can't figure that out just from this table. The table tells us that neutral nitrogen is a good nucleophile and that neutral phosphorus is a good nucleophile, but the table won't tell you which is the better nucleophile. So how do we determine which is the better nucleophile? Let's find nitrogen and phosphorus in our periodic table. We can see that nitrogen and phosphorus are both in the same column of the periodic table. Well, we've learned that when we're comparing neutral nucleophiles from the same column of the periodic table, nucleophile ability increases as you move down the periodic table. So because the phosphorus is further down in the periodic table, this pattern tells us that the phosphorus will be the better nucleophile. So we expect that reaction A has the better nucleophile because it's using the phosphorus, and therefore reaction A will have the faster SN2 mechanism. Here's our answer. We decided that reaction A will have the faster rate. We need to justify our answer. Well, we start the justification by saying that reaction A has the better nucleophile. That matters because this is an SN2 mechanism, and nucleophile quality does affect the rate for an SN2 mechanism because the nucleophile participates in the rate-determining step for SN2. For full credit, you probably need to mention the name of the mechanism in your answer. The professor is going to want you to see you talk about the name of this mechanism in your answer because we know that we would get a different answer for SN1. So make sure you identify in your answer that you've identified what the name of the mechanism is. This is SN2. Now we should also explain why the phosphorus is the better nucleophile. Well, we've learned that elements that are further down in the periodic table are better nucleophiles because they're more polarizable. The element further down in the periodic table is a better neutral nucleophile because it's more polarizable. We've discussed most professors in most courses, I think, would consider this to be enough of a justification, enough of an explanation for why reaction A is faster. So what are the key points for this problem? Well, most important, again, is switching gears back and forth between SN1 and SN2 mechanisms. Make sure you actually identify the mechanism, because we've seen that if this problem had dealt with SN1 mechanisms, the answer would be quite different. The answer would be quite different. Nucleophile quality does not matter for SN1 mechanisms, even though nucleophile quality does matter for SN2 mechanisms. So make sure you identify the mechanism. On this problem, we identified the mechanism by looking at the products and also by using our table, because the mechanism was not given in the problem. And you have to be able, the other skill that we needed on this problem was we had to be able to tell which of these was the better nucleophile. These are both good nucleophiles. These are both good nucleophiles, but how can we tell which is better? Because we know that this pattern for neutral nucleophiles, nucleophile ability increases as you move down the periodic table. So you would need to have that pattern memorized in order to get this problem correct. Notice that neutral nitrogen is a good nucleophile, but neutral phosphorus is even better. This problem also gave us another chance to practice how to think about SN2 mechanisms on an alkyl sulfonate rather than an alkyl halide. Let's take a look at this problem. This problem asks you to rank the leaving groups in these compounds from worst to best. Do you know how to answer this problem? This is a topic that I discussed in my SN2 video series. So if you watch that SN2 video series, you should already know how to answer this. If you think you know, you can pause the video and try to answer this question. Well, now let's go through this together. First, we need to identify the leaving groups. Well, we know that neutral iodide, neutral bromine, and neutral chlorine can be used as leaving groups. So it would be logical here to compare the leaving group ability of those atoms with the leaving group ability of the fluorine. So how can we compare these? Well, we can find fluorine, chlorine, bromine, and iodide all in the same column of the periodic table. So the question is, as we move down a column of the periodic table, what happens to leaving group ability? Well, it turns out that as you move down a column in the periodic table, leaving group ability improves. The elements that are further down in the column are better leaving groups. Elements further up in the column are worse leaving groups. So now we can compare these. Fluorine is the highest in the column, so fluorine would be the worst of our leaving groups. Iodine is lowest in the column, so iodide would be the best of these leaving groups. These compounds are already arranged in order from the top of the column and then moving down the column. Fluorine, chlorine, bromine, and iodide are already arranged in the same order that they're arranged in the periodic table. So this compound with fluorine would be have the worst leaving group. Chlorine would be the next better leaving group. Bromine would be a better leaving group than chlorine, and iodide would be the best of these leaving groups. That's how we can use this. As you move down a column, leaving group ability increases. Now, we know which of these are better and which are worse, but which of these would we classify as good leaving groups and which would we classify as unacceptable leaving groups? Well, actually, we've already learned how to think about that in previous videos. We've previously discussed that neutral chlorine, neutral bromine, neutral iodide, and neutral sulfonates are considered good leaving groups, and that other neutral atoms are usually not considered acceptable leaving groups unless you've specifically learned otherwise. Based on that discussion, we would say that neutral chlorine, neutral bromine, and neutral iodide would be classified as good leaving groups, and neutral fluorine would be classified as an unacceptable leaving group because it's not on the list of neutral leaving groups that we've learned. And of course, that's consistent with what we've learned from the periodic table. We did expect fluorine to be the worst of these leaving groups because it's the highest in the periodic table. In fact, it turns out that it's such a poor leaving group that it's usually not considered an acceptable leaving group for reactions. So notice that while chlorine is considered a good leaving group, bromine is even better than chlorine, and iodide is even better than bromine. But all three of these would be considered good enough leaving groups for an SN1 or SN2 reaction. The next thing I wanted to discuss is to compare this trend for leaving group ability with the trend we learned earlier for nucleophile ability. When we move down a column in the periodic table, leaving group ability improves. Do you remember what the trend was for nucleophile ability when you move down a column in the periodic table? Well, I hope you remembered that the trend for comparing neutral nucleophiles from the same column of the periodic table is the same as the trend that we just learned for leaving groups. When you move down a column of the periodic table, leaving group ability improves. And when you compare neutral nucleophiles moving in the same column of the periodic table, again nucleophile ability also improves as you move down a column of the periodic table. So it's important for you to have both of these trends memorized. Now, the next comment I want to make is that it is surprising. It is surprising that these trends both go in the same direction. Surprising. It's not what we would have predicted. If you knew this trend for leaving groups, the most natural prediction would be to predict that nucleophile ability would have the opposite trend and would increase as you move up the periodic table. Do you see why? Well, remember that leaving groups are electron receptors. Leaving groups act as electron receivers, but nucleophiles act as electron donors. So in a sense, a leaving group is kind of the opposite of a nucleophile because it does something different with electrons. They do different opposite things with electrons. Leaving groups are electron receivers and nucleophiles are electron donors, since in that sense, leaving groups are the opposite of a nucleophile. The most natural prediction would have been that the trend for nucleophiles should be the opposite of the trend for leaving groups. So it is surprising. It is surprising that leaving group ability and nucleophile ability both increase as we move down a column of the periodic table. That's not what we would naturally have predicted. Because this is surprising and it's not something you could have predicted just by thinking about it, it's important to memorize these trends. Make sure you memorize these trends because it would be difficult to figure these out just by thinking about it. Now, for the most part, I'm not going to try to resolve this contradiction, so to speak. I'm not really going to try very hard to explain why we got a surprising outcome here. I'll just encourage you to memorize these as an experimental fact. It's an experimental fact that the pattern for neutral nucleophiles is the same as the pattern for leaving groups, even though that's not what we might have predicted. But I do want to talk a little bit more about explaining the leaving group trend. The leaving group trend does make pretty good sense if we think about it on its own. So let's try to explain why leaving group ability improves when you move down a column in the periodic table. As you move down a column of the periodic table, leaving group ability improves. And the reason for that is that as you move down a column of the periodic table, atomic size increases. It turns out that larger atoms are better leaving groups. Larger atoms are better leaving groups. Well, then the next step is to explain that. Why are larger atoms better leaving groups? Well, to understand that, we need to use this idea. When judging leaving group ability, it is usually best to focus on what the leaving group will look like after it leaves. We want to think about what the leaving group will look like after it leaves to judge leaving group ability. Let's apply that to these examples. What would these leaving groups look like after they leave? You might want to pause the video and think about what would these leaving groups look like after they leave. Here's the answer. Here is what these leaving groups look like after they leave. And the most important thing to notice about what the leaving groups look like after they leave is that they each will have a negative formal charge. Remember that formal charges are the most important factor in organic chemistry, so when we see a formal charge, that's likely to be the most important factor to focus on. So what we want to ask is, which of these leaving groups will be best able to stabilize its negative formal charge after it leaves? Which of these can best stabilize the negative formal charge after it leaves? And the answer is the largest atom is best able to stabilize the negative formal charge because it has the most space to spread out the formal charge. I believe I've mentioned in the past that nature prefers charges to be spread out over a large area, and nature dislikes it, so to speak, when a charge is concentrated in a small area. It's better to spread out a charge over a larger area. Well, the largest atom, the iodide, the largest atom, has the most space to spread out the negative charge, so this negative charge will be the most stabilized. On the other hand, this fluorine is the smallest of these atoms. It has the least space to spread out this negative formal charge, and as a result, this negative formal charge will be the least stabilized. So now we have our understanding. Larger atoms are better leaving groups because a larger atom is better able to stabilize its negative formal charge after it leaves, and that makes it easier for the larger atom to leave in the first place. Here is that logic summarized. As we move down a column in the periodic table, leaving group ability improves. And here's the reason. As you move down a column in the periodic table, the atoms get larger. Well, a larger atom has more space to spread out its negative formal charge after it leaves. That means that for a larger atom, the negative charge will be relatively more stable, and that makes it easier for a larger atom to leave in the first place. That's why larger atoms are better leaving groups. Similarly, a smaller atom will have less space to spread out the negative charge that it's going to gain after it leaves. So on a smaller atom, the negative charge will be relatively concentrated and unstable. And since the negative charge after leaving on the smaller atom will be relatively unstable, that makes it more difficult for the smaller atom to leave in the first place. So the larger atoms are better leaving groups, and the smaller atoms are worse leaving groups. That explains why in this list, fluorine is the worst leaving group, because it's the smallest atom with the most concentrated and least stable negative formal charge after it leaves. Chlorine is a better leaving group than fluorine because it's larger. Bromine is a better leaving group than chlorine, and iodide is the best of these leaving groups because it has the largest atom, which is best able to stabilize the negative formal charge after it leaves, making it easiest for iodide to leave in the first place. Notice that we used this idea that when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. The key thing is that after these leaving groups leave, they're going to have to try to stabilize this negative formal charge. So the best leaving group is going to be the atom that will be best able to stabilize that negative formal charge. We have seen that when we're comparing leaving group ability for elements from the same column of the periodic table, the key factor to focus on is atomic size. A larger atom is a better leaving group. Now, some leaving groups consist of an actual group of more than one atom. But this rule is based on the atomic size of the specific atom in the group that will be gaining electrons. The rule does not refer to the size of the entire leaving group as a whole. A larger atom is a better leaving group, but you should not assume that a larger group of atoms will be a better leaving group. I will discuss this distinction between atomic size and the size of the entire leaving group a little bit later in this video. Please pause the video and try this problem. Now we can discuss. Let's number the carbons. There are no ionic bonds to discover. We should identify roles. There are no negative atoms to play the role of nucleophile, so we can use this neutral oxygen as our nucleophile because of its lone pair. Remember that ET stands for an ethyl group, so this molecule is ethyl alcohol. We would expect neutral bromine to be a leaving group, and we would expect neutral iodide to be a leaving group. So we would expect carbon 3 to be a alpha carbon in both reactions. Now we can determine the mechanism. Now we are not going to use the table to determine the mechanism for this problem because this problem told us the mechanism to focus on in the problem. So we know from the information in the problem that we should focus on SN1. Write down what mechanism you're focusing on, so we don't need the table for that. So which of these will be the faster SN1 mechanism? Well, it doesn't help to compare the nucleophiles because both reactions have the same nucleophile. It doesn't help to compare the alpha carbons because both reactions have a secondary alpha carbon. The difference between these two reactions is the leaving groups. So that's what we need to compare to determine which of these leaving groups is the better leaving group. Well, wait, does that even matter? Does leaving group quality affect the rate for an SN1 mechanism? Yes. In the previous video, we learned that leaving group quality does affect the rate of an SN1 reaction. The leaving group participates in the rate determining step for SN1, so using a better leaving group will increase the rate for an SN1 reaction. In fact, we saw that leaving group quality matters both for SN1 and for SN2. So whichever reaction has the better leaving group will be the faster SN1 reaction. Now, how can we tell which of these is the better leaving group? Well, we know that both of these would be considered good leaving groups. We have seen in the past that both neutral bromine and neutral iodide are on our list of good leaving groups. But how can we tell which is better? Well, we discussed how to handle that issue previously in this video. We should locate bromine and iodide in our periodic table. Here's bromine and here's iodide in the periodic table. We can see that they're in the same column of the periodic table. And we have previously learned that when you're comparing elements from the same column of the periodic table, leaving group ability improves as you move down a column. That tells us that the iodide is the better leaving group. And bromine is the worse leaving group. Bromine is still considered a good leaving group, but it's not as good as iodide. So that tells us that reaction B will be faster because it has the better leaving group. Here is our answer, or the beginning of our answer. We've decided reaction B will be the faster reaction. Remember, we must justify our answer. So we can start our justification by saying that reaction B is faster because iodide is a better leaving group than bromine. Now, some professors might consider that enough justification. Some professors might give you full credit for this justification. But I think maybe other professors would want further justification for why iodide is the better leaving group. So here's some further justification. Iodide is the better leaving group because iodide is a larger atom than bromine, which means the iodide is better able to spread out and stabilize its negative charge after it leaves, which makes it easier for the iodide to leave the alpha carbon in the first place. This is probably a little more justification than most professors would require, but in any case, here we've given a good justification for our answer. So what did you need to know in order to be able to get this question correct? Well, you had to know that leaving group ability matters for the rate of an SN1 mechanism. But remember that leaving group ability also matters for SN2 mechanisms. Leaving group quality matters both for the rate of an SN1 reaction and for the rate of an SN2 reaction, because the leaving group participates in the rate determining step both for SN1 and for SN2. So then you had to be able to figure out which of these was the better leaving group. Again, both bromine and iodide, they're both considered good leaving groups. But to figure out which is better, we had to notice that they were both in the same column of the periodic table. And you need to know that when comparing elements from the same column, leaving group ability improves as you move down a column. Pause the video and try this problem. Now let's discuss. We can label some roles. We expect this iodide to be a leaving group, this bromine to be a leaving group, this neutral bromine to be a leaving group. So we would expect this to be an alpha carbon, this to be an alpha carbon, and this to be an alpha carbon. We don't need to use the table to determine the mechanism. The problem told us the mechanism. Write down that the mechanism will be an SN1 mechanism. Notice we're not using the table for that. We're using the information in the problem. The table would not tell us to focus on SN1, say, for this molecule. The table certainly wouldn't tell us to focus on SN1 for this molecule, but we are focusing on SN1 for all three of these molecules because of what the problem told us to focus on. Now we need to start trying to compare these molecules. When we're comparing, we have to ask how the molecules are different from each other. Well, obviously, one way they're different is that they have different leaving groups. So one issue we're going to be focusing on is leaving group ability. But notice that's not the only way they differ. They also differ in their alpha carbons. This is a secondary alpha carbon. This is a primary alpha carbon. And here again, we have a secondary alpha carbon. So it looks like we're going to have to focus not just on the leaving groups, but also on the alpha carbons. The fact that we have two factors to think about might make this a more complicated problem. Now, we have to decide which of these molecules to compare first. For example, should we start by comparing the first and the second molecule? Well, the principle is that comparisons are easiest when the molecules are the least different. The easiest comparison to make is between molecules that have the fewest differences. So we want to compare the molecules with the fewest differences. That means that comparing this and this molecule is a poor comparison. This would be a poor comparison because these differ in too many ways. The first and the second molecule have different leaving groups, and they also have different alpha carbons. Since they have both different leaving groups and different types of alpha carbons, they're going to be more difficult to compare. So let's not try to compare these two molecules unless we have to. Instead, here's a good comparison. Let's compare the first molecule and the third molecule. These only differ in one way. The only difference between the first and the third molecule is their leaving groups. They have the same alpha carbon. So since there's only one difference between the first and the third molecule, those are good ones to compare. And for the first and the third, we can just focus on comparing the leaving groups. Does leaving group quality matter for an SN1 mechanism? Yes. We know that leaving group quality does matter for an SN1 mechanism. So whichever of these has the better leaving group, that will be the faster SN1 mechanism. Leaving group quality does matter for the rate of an SN1 mechanism. Which of those has the better leaving group? Well, you should know that iodide is the better leaving group than bromine. We have discussed that when you compare elements like bromine and iodide that are in the same column of the periodic table, leaving group ability improves as you move down a column. So since iodide is further down in the column, iodide will be the better leaving group. So we can say that this compound will have the faster and this compound the slower SN1 mechanism. So now we're starting to rank these compounds. Notice that when we rank them, the problem told us to rank starting with the fastest and ending with the slowest. So here on the left I put the faster, and here on the right I put the slower. I made notes to myself to help me remember that this end is the faster end and this end is the slower end. And I've left gaps between these molecules because I'm not sure where to put the third molecule yet. I'm not sure if I'm going to want to put the third molecule here, here, or here. But so far we know that this molecule will have a faster SN1 than this because this has the better leaving group. Okay, and now we need to make a comparison involving this middle molecule. Now, what comparison should we make? Should we compare this middle molecule to this one? Well, no, that's not the best comparison because these two molecules differ in two ways. These two molecules have different leaving groups and also different types of alpha carbons. That'll make the comparison more complicated. It'll be easiest if we make a simpler comparison between molecules that differ in fewer ways. These two molecules differ in only one way. These two molecules have the same leaving group. They both have a bromine leaving group. They only differ in their alpha carbons. So the simpler comparison is to compare these two based on their alpha carbons. We know that this is a secondary alpha carbon, and this molecule has a primary alpha carbon. Well, we've learned that the more substituted alpha carbon is better for SN1 because it'll form the more stable carbocation intermediate. So I'll write this molecule in this position to show that it's going to have a slower SN1 rate than for this molecule. Remember, here's the order that we've learned for SN1 rates and alpha carbons. We've seen here that the rate of an SN1 reaction is faster for more substituted alpha carbons and slower for less substituted alpha carbons. In particular, we saw that a secondary alpha carbon would have a faster SN1 rate and a primary alpha carbon would have a slower SN1 rate. Remember, the reason for that is based on stabilizing the carbocation. A secondary alpha carbon will form a more stable secondary carbocation, and a primary alpha carbon could only form a highly unstable primary carbocation. Secondary alpha carbons are better for SN1 than primary alpha carbons. That's why this SN1 reaction will be faster and this SN1 reaction will be slower. So now we've completed our ranking and we can put in our numbers. We can say this will be number 1. Remember, we want number 1 to be the fastest SN1, then number 2, then number 3. So in the original molecules, we can say that this molecule will be number 1, the fastest. This molecule will be number 3, the slowest. And this molecule will be number 2, in the middle. What did you need to know to get this problem right? What were the key skills that we needed for this problem? Well, let's see. First of all, it was really crucial to know what mechanism we were focusing on. We didn't use the table to determine the mechanism. We used the problem. The problem told us to focus on SN1. Why did that make such a big difference? Well, of course, leaving group quality would matter for either SN1 or SN2. The trend for leaving group quality would be the same for either an SN1 or an SN2 reaction. Either an SN1 or an SN2 reaction will be faster with a better leaving group. But notice that we have very different alpha carbon trends for SN1 and SN2. For an SN1, the more substituted alpha carbon gives the faster reaction. But for SN2, the less substituted alpha carbon gives the faster reaction. So it was crucial for this problem that we saw that we were dealing with SN1 and not SN2. The answer would have been quite different if we were focusing on an SN2 mechanism, because the pattern for alpha carbons is quite different for SN2 reactions than for SN1. So always make sure you know what mechanism you're focusing on for each of the problems that you'll be dealing with on your exams. Write down the mechanism that you are focusing on. Again, we had to use the idea that as you move down a column in the periodic table, leaving groupability improves as you move down a column. That's how we knew the iodide was the better leaving group than the bromine. Now again, this might be a tricky problem for some people because there are multiple comparisons to make. So remember the techniques we used here. We tried to compare the molecules that had the fewest differences. We compared this molecule and this molecule. That was a good comparison because they only differed in leaving group. They had the same type of alpha carbon. And we compared this molecule and this molecule. That was a good comparison because these two molecules had the same leaving group. These two molecules only differed in their alpha carbon. On the other hand, we did not focus on comparing this molecule and this molecule. That was not the most helpful comparison because these molecules differ in two ways. They have different leaving groups and different alpha carbons. That makes that a less helpful comparison. So when possible, focus on comparing pairs of molecules that differ in only one way. That was something that we were able to do to simplify our work here. Also be very careful to get the ranking correct. This problem asked us to rank in order of decreasing reactivity, but you might see other problems that would ask you to rank in order of increasing reactivity. So pay close attention. On this problem, number 1 was the fastest of the molecules, but you might see another problem where number 1 should be the slowest. So the best thing to do, notice that when we wrote down this ranking, I reminded myself that this was the end of the ranking for the faster molecules, and this was the end of the ranking for the slower molecules. Write down notes to help you avoid getting confused, such as that this is the faster end of the ranking and this is the slower end of the ranking. Finally, I'll mention that if you actually looked at your table, you would notice that the table would actually predict no SN1 reaction at all for this molecule. We don't usually predict SN1 at all for a primary alpha carbon, but that's no difficulty or no problem. That's why we said that SN1 would be slowest in this case. It wouldn't necessarily be 0. All we're saying is that SN1 would be so slow for this molecule that it wouldn't be a particularly practical reaction. I don't know if the rate would literally be 0, but whether the SN1 rate is 0 or just very low for this molecule, this would certainly be the slowest SN1 reaction rate of these 3. Please pause the video and try this problem. Now let's discuss the solution. Let's start by numbering. Be sure to number the products so that your numbers are consistent with the numbers for the starting materials. We're already given the formal charge here. There's no ionic bonds to find formal charges. We're given some formal charges. We can identify roles. This negative formal charge indicates that the N3- will play the role of nucleophile. We identify neutral chlorine as a good leaving group. Now, this molecule does not seem to have any acceptable leaving groups. The OH is the closest that we have to a leaving group, though, and we can see that the OH is playing the role of leaving group by comparing the starting materials to the product. You can see that the OH is leaving carbon 2. So even though we wouldn't normally consider OH a good leaving group, we're going to consider OH as a leaving group for reaction B. That makes carbon 2 into our alpha carbon. The ETOH is ethyl alcohol, which is the solvent. We are not going to use this solvent as the nucleophile for this problem because we have a better nucleophile present, the N3-. Now we identify the mechanism. The mechanism was not provided by the problem. First step for identifying the mechanism here is to compare the products with the starting materials. By comparing products and starting materials, we can see that these are both substitution reactions, where the nucleophile is substituting into the position formerly occupied by the leaving group. But in order to tell whether this is SN1 or SN2, we need our table. Carbon 2 is a primary alpha carbon, which puts us in the top row of the table. Our nucleophile is N3-, which puts us in the middle column of the table. Notice that N3- is a special nucleophile which is different from an ordinary N-. So the table predicts an SN2 mechanism. Write down the name of the mechanism. So which of these would be a faster SN2 mechanism? Well, it doesn't help to compare the nucleophiles because both reactions have the same nucleophile. It doesn't help to compare the alpha carbons because both reactions have a primary alpha carbon. Instead, we need to compare the leaving groups. And as we already mentioned, we should already know that chlorine is a good leaving group, and this OH group is a bad leaving group. We have seen that neutral chlorine, bromine, iodide, and neutral sulfonates are good leaving groups, while other neutral atoms are usually not acceptable leaving groups. So for this problem, we know that the neutral chlorine is a good leaving group, but that the neutral OH group is not an acceptable leaving group. Does that make any difference? Does leaving group quality matter for an SN2 mechanism? Yes. The leaving group participates in the rate-determining step for SN2, just like it does for SN1. So the leaving group quality affects the rate of an SN2 reaction, just as it affects the rate of an SN1 reaction. And in fact, we know that an SN2 reaction requires a good leaving group, just like an SN1 requires a good leaving group. So not only will reaction A be a faster SN2 mechanism, but in fact we would expect that the rate for reaction B would be close to 0, because this is a bad leaving group and SN2 requires a good leaving group. Our answer is that reaction A will be faster. Be sure to justify your answer. Our justification is that chlorine is a better leaving group than OH. I think most professors in most introductory courses would accept this as a sufficient answer for this problem. As I mentioned, in fact, the rate of reaction B would be close to 0 for this problem because SN2 requires a good leaving group and OH is a bad leaving group. So what do you need to know in order to get this problem correct? Well, you need to know, be able to identify that chlorine is a good leaving group and that neutral OH is a bad leaving group. And you need to know that leaving group quality affects the rate for an SN2 mechanism. Leaving group quality affects the rate both for an SN2 and for an SN1 mechanism because the leaving group participates in the rate determining step, both for SN2 and for SN1. Here's a problem to review what we've been discussing, some of what we've been discussing in this video. Please pause the video and answer both part A and part B for this question. Here's the answer. What we have learned is that the pattern for leaving groups is the same as the pattern for neutral nucleophiles. Leaving group ability increases as you move down a column of the periodic table. And the same thing is true for nucleophile ability for neutral nucleophiles. For neutral nucleophiles, nucleophile ability increases as you move down a column of the periodic table. Now, remember that you need to memorize this trend because it's not probably what we would have predicted. You probably would not have predicted that the nucleophile trend would be the same as the trend for leaving groups. After all, in a sense, a leaving group is the opposite of a nucleophile because a leaving group receives electrons, whereas a nucleophile donates electrons. Since they're opposites in that sense, it might have seemed natural to predict that the trends for moving in a column of the periodic table would be opposite for a leaving group and for a nucleophile. But experimentally, it turns out that surprisingly, the trend for neutral nucleophiles is the same as the trend for a leaving group. And since that's not what we might have predicted, we simply have to memorize this experimental trend. Now remember, we said that the reason for this trend for nucleophiles is based on this idea of polarizability, which you can learn more about in your textbook. And the reason for this trend for leaving groups we discussed earlier in the video. It's based on the idea that elements that are further down in the periodic table are larger. And therefore, after they leave, they're better able to spread out and stabilize their negative charge after they leave. And therefore, it's easier for these larger atoms to leave in the first place. Well, we have seen that for the situations we have discussed in this video, the key factor to focus on was the atomic size of the elements. Notice that we have not been focusing on the elements' electronegativities. But of course, there are other situations in which you should focus on electronegativity. For example, when you're comparing different elements from the same row of the periodic table, in that situation, you should usually focus on electronegativity. In this video, we have focused on comparing leaving groups and nucleophiles with elements from the same column, because that tends to be more frequently tested than comparing elements from the same row. But you should be able to find a discussion in your textbook of how to use electronegativity to compare reactivity for elements in the same row. And for completeness, I will also mention that there are some situations different from the ones discussed in this video, in which you should focus on electronegativity even when you're comparing elements in the same column. That usually occurs when you're considering how well an element can stabilize the negative charge on a nearby atom rather than on itself. But for the sake of simplicity, we will not be discussing those situations in any detail in this video. Now let me warn you against a mistake that I sometimes see students make after they learn this material. We've learned that when you're comparing two elements from the same column of the periodic table, the element with a greater atomic size will be the better leaving group. That's true. But notice it's only the atomic size that matters. Only the size of the leaving group atom affects leaving group ability. The size of the entire leaving group as a whole does not directly affect leaving group ability. Let me show you what I mean by that. Which of these molecules has the better leaving group? Well, you should know that this molecule is an alkyl sulfonate, and therefore it contains a good leaving group. Whereas an ordinary neutral oxygen is not in our list of good leaving groups, so this would be an unacceptable leaving group. Now, why? Why is this sulfonate a good leaving group, whereas this neutral oxygen is a poor leaving group? Well, here's the wrong answer. After learning the previous material, sometimes students will tell me that the sulfonate is a better leaving group because it's bigger. This group looks bigger than this group, so some students wrongly tell me that this is a better leaving group because it's bigger. But remember, that's a wrong explanation. Because remember, only the size of the only atomic size of the leaving group atom affects leaving group ability. The size of the entire leaving group as a whole does not directly affect leaving group ability. The specific leaving group atom here is the oxygen. That's the one that's going to leave the alpha carbon. And the specific leaving group atom here is also an oxygen. The size of the leaving group atom that's going to actually gain the negative formal charge is the same for both of these pictures. In this case, this oxygen will gain the negative formal charge, and in this case, this oxygen will gain the negative formal charge, and those two oxygens have the same size. The size of the leaving group as a whole doesn't really matter. So you should not say that this sulfonate is a better leaving group because it's bigger than this alcohol group. That's not the correct explanation. Do you know what is the correct explanation? Why is a sulfonate group a better leaving group than an alcohol? Can you answer that question? This is actually a topic that I discussed in my SN2 reactions video series. Well, remember that to judge leaving group quality, we should probably think about what the leaving groups will look like after they leave. Here's what these two leaving groups would look like after they leave. After they leave, when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. After they leave, these leaving groups will have gained a negative formal charge. So whichever group is better able to stabilize the negative charge after it leaves will find it easier to leave in the first place. Well, the sulfonate will have the more stable negative charge, but it's not because the group is larger. Remember that the size of the entire group is not what's relevant. The only sizes we would compare are the sizes of these two oxygens, the oxygens that bear the negative charge, and those are the same size. So it's not the size that makes the difference here. This leaving group is more stable after it leaves because its resonance stabilized. This negative charge is resonance stabilized, which makes it easier for this oxygen to leave in the first place. This leaving group has no resonance stabilization, which makes it difficult for that oxygen to leave in the first place. So now I've drawn in the electron pushing arrows to show the two other resonance structures that this leaving group possesses after it leaves. And you can see that the resonance allows this negative formal charge to be spread out among three different oxygens. The negative charge is spread out between this oxygen, and this oxygen in three different resonance structures. Well, remember, negative charges are more stable when they're more spread out. So the sulfonate is better able to stabilize its negative charge after it's left, which makes it easier for the sulfonate to leave in the first place, making the sulfonate the better leaving group. This oxygen has no potential for resonance stabilization, which means that it's more difficult for this oxygen to leave in the first place, making it the worse leaving group. And in fact, again, an alcohol is considered a bad leaving group. So a sulfonate group is a good leaving group because its negative charge will be resonance stabilized after it leaves. Again, it's not because it's a big group. The size of the entire leaving group as a whole isn't really significant. Only the atomic size of the specific atom that receives electrons affects leaving group ability, and that's a criterion that's not relevant for this example, because in both cases we have the same atom receiving electrons and oxygen. Notice this is another example of the idea that when judging leaving group ability, it's usually best to focus on what the leaving group will look like after it leaves. And remember that the point that we just made about leaving groups also applies to nucleophiles. We've seen that for most of the situations we've discussed in this video, the key factor to focus on was atomic size. The trend for nucleophiles is based on the atomic size of the specific atom that donates electrons, not on the size of the entire nucleophilic molecule. And as we saw here, for leaving groups that consist of more than one atom, the trend is based on the atomic size of the specific atom that receives electrons, not on the size of the entire leaving group as a whole. Let's try a review quiz. Please pause the video and answer these questions. I hope that you actually really did try these problems. It would be good to write these definitions down on paper. Here's the answer. You should have known that the 5 roles are nucleophile, electrophile, leaving group, acid, and base. And I hope that you attempted to give 2-part definitions for each role. It's not good enough to say that a nucleophile donates electrons. You have to say that the nucleophile donates electrons to join an electrophile. Otherwise, you can't tell the difference between a nucleophile and a base, because they both donate electrons. Again, give 2-part definitions. It's not good enough to say that an acid gives away a proton. You also need to know what it's doing with its electrons. So you need to know that an acid receives electrons and gives away a proton. And I guess in a way, most of these are three-part definitions because the definition also includes what that role reacts with. You should know that nucleophiles react with electrophiles and that bases react with acids. So I hope that you're trying to learn these definitions pretty much word for word, because these are the most useful ways to think about the definitions of these roles in Ochem. Your success in organic chemistry absolutely depends on having complete mastery of these roles and these definitions. So keep reviewing these roles and these definitions however many times is necessary to make sure that you have complete mastery of these definitions. These roles will be fundamental to your success throughout both semesters of your organic chemistry class. Remember that one way to improve your skill with these roles is you should be trying to identify and think about these roles for pretty much every organic chemistry problem. For this problem, for example, we were careful to identify the nucleophile, the leaving group, the electrophile, the acid, and the base for each step. And I hope that you're trying to carry that out for every mechanism that you carry out now. Try to identify all the roles that are participating in each step. I know it might feel like that's going to slow you down, but that's an important tool for getting the mechanism correct. And if you keep practicing that skill, you'll get much better mastery of the meanings of those 5 terms. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.